Your presenter today is Luis Gonzalez. He is the Senior Manager for Refining, Deflaking, and Dispersing at Valmet. After getting his BS in Chemical Engineering, Luis worked at a recycled tissue manufacturer for several years in progressively responsible roles, including Technical Director and leading the Quality Control, Engineering, Design, and Safety departments. Luis moved to GL&V and became a Valmetier with the recent acquisition of GL&V. Luis is an expert in the area of refiner optimization and performance. Luis will start off today with an overview and discussion of refiner basics. He will continue by looking at maintenance, process control, and remote support. Finally, he will discuss how to partner with Valmet to maximize refiner performance. At the end of his section of the presentation, we'll allow 10 to 15 minutes of time for questions and answers. Now it's over to Luis.
Thanks, Ward, and welcome everyone. I have a good amount of material to cover, so we'll get started right away. Before we get into details on maximizing refiner performance, I'll take a couple of minutes to discuss some of the refiner basics. So I'll start with a simple question. What are refiners used for? And the simple answer is to modify fiber into a more usable form. Structure of the preconditioned fiber in turn dictates finished product characteristics and limitations. And here I've listed a couple of the properties that refining impacts, things like tensile, tear, opacity, formation, burst. All that is impacted by refiners. So let's go a little deeper into the refiner and see what's actually happening inside the refiner. So you have two opposing plates crossing on top of each other, pulp going through them, and every time bar edges go on top of each other, flocks of fiber accumulate and get compressed, and then they release as the grooves go on top of each other. So you have this continuous compressing and releasing as pulp continuously passes through the refiner plates. And this is what's causing that change in the fiber characteristics. What is actually happening to the fiber? Well, it's fibrillating externally, it's fibrillating internally, and or the fiber is being cut. These are the changes that we're looking for within the refiner. At the end of the day, going back to the original question, what are refiners used for? This concept of refining is very critical to the overall operation of the paper machine because it dictates the fiber properties and thus the sheet characteristics going on the actual paper machine. So we're impacting the paper machine performance and the end product quality. How we deliver that pulp to the refiners and out of the refiner and the way that we control the refiners is therefore extremely critical to all finished product quality and performance. So before we get too far into it, I wanted to bring up a couple of critical components that I'm going to be discussing just to define them. And we'll start off with the adjusting mechanism. This is the door assembly on a refiner, and it's what's used to apply the power onto the fiber. So within that adjusting mechanism, one of the stator positions in the refining zone is called a sliding head. And this is what's actually moving. So the door is stationary, but the sliding head moves in and out to change the plate gap and press the fibers more or less, meaning applying more or less power. And we have this concept of tram alignment, which means what is the perpendicularity of the shaft relative to all refining surfaces. So what we're trying to achieve is that the four plate positions are all parallel to each other, so assuring that the shaft is perpendicular to the door surfaces ensures that the rotor is also parallel to the door surfaces because it is perpendicular to the shaft. And we have the rotating assembly, and this is the piece of equipment that's transferring the rotation from the main motor onto the refiner. The hub, this is a stationary piece on the shaft that holds the rotor and the rotating plates on the rotor. And then the rotor, or the actual movement inside the refiner that cause that pumping action and bar edge crossings to cross on top of each other. Those are the key components that we're going to be discussing. I figured I'd start with a bit of an explanation on them. So now we'll move on to the maintenance portion of this presentation. Safety first. I'm not going to get into a lot of details on this slide. Whoever requests will have this available, and there are more interlocks. But the important thing to note here is that every refiner is designed to a specific pressure rate. Going beyond that is unsafe for the refiner and obviously those around it. So we have interlocks in place that we definitely want to keep and maintain, test and assure they are working properly before we start up any refiner operation. And throughout the life of the refiners, we need to make sure that these are comprehensive and working properly. So in specific, you can see here that our refiner is designed for 100 PSI. As door surfaces and door closures start wearing, maybe we derate that a little bit. But in general, we're looking to maintain pressures within this refiner at a controllable rate, well within that 100 PSI, so that we make sure, again, that the refiner is safe and those around it are as well. This is a traditional cantilevered design in which pulp is coming in. You can see here at the 12 o'clock and going out at the 12 o'clock, you have power being applied in this direction. So as the gap closes here, this rotor is free to move about, and it's going to try to balance itself between the two stator positions. The ultimate goal of any double disc refining operation is you want to make sure that this rotor is perfectly balanced between the two stator positions. If not, imagine this rotor being closer to this side than this side, and you get super refining on one side, little refining on the other side, and the combination of that is never going to be as efficiently refined as if both sides were equally the same gap. What are some of the points in the refiner that are hindering this from happening that we need to make sure we address on a regular basis and check on a regular basis? Well, if you imagine the shaft is moving side to side on this traditional cantilever design, and you have a floating shaft that has a packing sleeve that's touching some of the refiner components. If you can imagine this being scored, grooved, in bad shape, this is going to catch onto a different part of the refiner, and so that rotor isn't going to be free to move about and perfectly balance itself. So sometimes you apply more power, it moves, other times it won't move. If you over grease a coupling, you're going to freeze it in place. So in general, we recommend oiling the main motor coupling, but some customers do decide to grease it, and that's acceptable as long as it's hand packed and not pressed in there such that it freezes in place. And finally, in this traditional floating shaft design, all the movement is happening on this actual main motor coupling. So if it's in bad condition, the rotating assembly isn't going to be able to float properly on top of it. And if the rotating assembly isn't floating, the shaft isn't floating, and so the rotor is not floating and not centering. So these are components we're looking at making sure that they're in good condition and inspecting them at least once a year. We want to make sure that we get inside that refiner at least once a year and check these points out. Now, the traditional 3000 has a couple of more points that come in contact as that shaft moves from side to side. So as the rotor is trying to balance, the shaft has a couple of grease points that we need to make sure are well lubricated at all times to make sure that we keep that refining efficiency at optimum. So here are a couple of other grease points that we're looking at. In the traditional DD4000 and now the latest and greatest DD6000 series refiner, we've eliminated a lot of that heavy metal, and there's not a lot of interfacing between the shaft and other components. So the two major components are, again, the coupling and the packing sleeve. But we do want to check every 3 months to make sure that the oil is not running hot, that the oil is running well, and change the oil on this rotating assembly to actually make sure that the refiner is rotating properly and not freezing up in place during operation. So these are the critical things that are associated with the traditional floating shaft cantilever design refiner. One of the main improvements, a definite step change improvement in double disc refining was the invention of spline technology. So spline technology, what it did was now the shaft is frozen in place. There's no need for this whole component to be going back and forth for the rotor to perfectly balance itself. Everything is now happening inside the refining cavity. You have one component, the rotor, floating on top of a fixed hub, and that hub is fixed onto the shaft, which again is fixed in place. So now we can look at non-lubricated disc couplings. The coupling is no longer an issue that's going to impact refining efficiency. We can look at potentially mechanical seals, other types of sealing. The packing sleeve isn't going to impact refining efficiency. Again, these are mechanical issues that must be dealt with for other reasons, but in terms of refining efficiency and refiner operation, those are no longer hindering spots for the rotor balancing itself and thus do not impact refining efficiency in and of itself. But here's what these splines look like. You have, again, this hub is fixed onto the shaft. Shaft is fixed in place, so nothing is moving. You have this rotor, and these teeth interlock on these teeth, and you have movement back and forth as power is being applied and flow changes. This rotor is going to perfectly balance itself between the two stators without any hindrance from any of the previous mechanical issues. We went a little bit further and said, well, if the flow ports were on the rotor, then as the flow came into the refiner and hit one of these dead spots here, the rotor would be bouncing back and forth. So let's eliminate that possibility as well and move that onto the hub. So now the hub has the flow ports where traditionally they were on the rotor. We designed this spline component to have two life cycles. So this is always rotating in one single direction. And so the wear pattern is in a single direction. We have a tolerance for these spline components in which we believe that they're going to be effective and the refining efficiency is such that it's going to flow properly and balance itself perfectly throughout that tolerance. But once you achieve that tolerance, you can flip both components 180 degrees and start that same wear pattern in the opposite direction. So we're getting two life cycles out of these guys. And we're looking at somewhere between 10 to 15 years of life before you have to start looking at changing any one of these components. And when we change one, we change them both. So what's in it for me? Well, this huge step improvement that we made results in somewhere between 10 and 20% less energy needed to achieve the same or better fiber strength development. So we're looking at better pulp at higher freeness going out of your refiner. You're applying less energy, so you're dropping the freeness less. And because now the rotor is perfectly balanced, whereas before there were all those mechanical issues associated with it potentially balancing itself, you're getting the same plate wear on both the stator and rotors, meaning on the door side and on the motor side. So plate life is substantially improved as well. We need to make sure that we don't say, let's put a spline in there and forget it. No, the spline also needs to be taken care of. And every time we're opening up the refiner to change out the refiner plates, we need to make sure that these splines are in good condition. We're checking for burrs, dins, anything that can impact the rotor from perfectly floating on top of this hub is going to be a point that we want to make sure we polish out, we clean out, and we make sure that it can by hand float properly. We also want to make sure at least once a year that we're checking the wear. If you can see over here, this is the wear pattern of the hub on the rotor. There's a step that you can clearly see over here. So this is what I'm talking about. Once this reaches 100 thousandths of an inch wear, then it's time to flip both components around and start the same wear pattern on the other side. This is a wear on one side, so this component has not yet been flipped. Again, all the movement is now happening inside the refining cavity, the refining zone, and it's all happening in here. So we need to make sure that this component is now in tip-top shape to make sure that refining efficiency is kept as high as possible. So going beyond the actual spline components, and this is now looking at both the traditional floating shaft design and spline designs. At the beginning, I mentioned that within the refiner, two opposing plates are going on top of each other to compress and then release fibers on them. So we need to make sure that the actual surfaces are all parallel to each other. So how can we assure that? What are we looking for? So this is a once a year event as well. This is what I defined at the beginning, this tram alignment, in which we're trying to make sure that the main door surface here, this is what we call our zero target. This is what we machine perfectly parallel, and everything else needs to be machined to this door, is parallel to the rotor. So here we're trying to check to make sure that there is perfect parallelism between the rotors and the stator position on the motor side. So once that is fixed, you also want to tram the door side and make sure that that has no issues. Now, some of the issues that we do see on the door side is washed out adjusting mechanisms and things of that nature that we sometimes try to compensate with sealants. And what we're doing is kind of putting a Band-Aid on a bullet wound. You're not seeing the bleeding on the outside, but you're dying on the inside. So we no longer have a surface that we can measure to make sure everything's parallel. We're just hoping that every time we close the door and we seal it, things are happening the right way, and there's no right way to measure things if they can't be measured. So there's no real way of knowing whether it's happening as you want it to happen or not. And this is when it's time to start thinking, okay, it's time to change out my adjusting mechanism, or it's time to change out my whole refiner, because there is no way for me to understand how good I'm doing other than the fact that my plates started out with 3 months life and now they're down to 10 days. Something that we want to look at once a year as well. The actual movement of the sliding head on the adjusting mechanism happens through a set of gears. So this is another component that we want to be sure are working properly, and it's a once in a year event as well. We're looking to make sure that when this stator positioned door, this is all cantilevered against the main housing, we fix that in place and we measure to see how many turns of backlash there are before you actually start getting movement of the sliding head. This is the only component that actually moves inside the refiner, the sliding head back and forth. We want to see how many turns of backlash the refiner has, or how many turns it takes before there's actual movement in the sliding head. So if you can imagine, you're in operation and your flow changes, so your energy changes, and you try to compensate by applying a little bit more power, but 4 turns of backlash and you still haven't reached this target that you're shooting for, then you've had all that pulp go forward at improper energy levels, and so you have variability in your paper machine. So this is what we're trying to look at, making sure that these components are in tip-top shape to make sure that refining efficiency and refiner performance is optimal. Now the sliding head in and of itself, we need to make sure that it easily moves inside the adjusting mechanism. So there's some grease points, very easily accessible. But we also need to look once a year to make sure that the surfaces inside are machined properly and that everything is where it's supposed to be, and that the sliding pads are also in good condition so that when it says it's moving back and forth, it's actually moving parallel to everything and not just bobbling up and down. So these are all components we're looking at. After a certain time, and this is roughly 5 years, we're saying, hey, it's time to just let it go. There's nothing more we can do about it. No matter how well we're maintaining and changing the oil, it's time to start thinking about changing out the rotating assembly and the adjusting mechanism. This is a kind of a 5 to 7 year, sometimes less, sometimes more, in which we want to just swap out the adjusting mechanism with either a refurbished or a new one. And what we would do is send you a rotating assembly. You install it, send back the old shell, and you're ready to go. We rebuild the old shell and make it accessible to somebody in the near future. And then at about 10 years, you're looking at it's time to maybe look at overhauling, rebuilding the whole refiner. And here's a couple of pictures of old going to new. This is when it's time to just look at the whole thing and say, hey, done my best. 10 years is a great time to start thinking about, let's rebuild this whole thing, start all over, and make sure that my refining efficiency stops dropping. So there's a lot of things going on that impact refiners, the amount of energy, the type of material, the refining system, whether it's batch or continuous. So all of these are taken into consideration, but are we using the correct plates for the particular application? And that's something that we need to address each time and specific for each application. So each one of those parameters that you saw on that last page briefly are impacting the selection of the refiner plates to get the right properties for your finished good. So there's a whole bunch of potential selections of refiner plates, a lot of geometries depending on what kind of refiners you have out there. We have another webinar in January that Artina is going to be giving, so stay tuned for that one, and she'll get into a lot more details on this than I will right now. The main point to take from here is that definitely this is one of the high impact points on refining efficiency. The proper plate selection is extremely important. There is not enough time in this seminar to discuss this one in as much detail as needed. And finally, on the maintenance side, is making sure we're able to remove those plates on a timely manner and safely. So in the past, you had 17 guys out here trying to change a refiner plate, one pushing, the other one holding something up, and then you had an overhead crane holding up a segment while 3 people were standing under it. So we made life easier with this rotor removal arm. You're changing out the door side plates, then you're swinging in this rotor removal arm into the refiner and grabbing the rotor, and you're changing the motor side plates very quickly here. Once you're done, you close it back up, swing the arm out, close the door, and all is said and done. So this is refiner maintenance 101. Again, each one of these components has an expected life that we're hoping that each and every one of you is checking to make sure they're in tip-top condition. We also have experts out in the field that we can help with inspections on a regular basis. But from here, I'm going to jump on to process controls. So this slide is a little bit busy, but the main goal is there's lots of ways in which customers operate their refiners, some better than others. Traditionally, it was amps. And a step improvement was, okay, let's control through constant power. Then came this energy control, and finally, Freeness control with cascading energy controls. The important thing to note here is that the way we transfer energy onto the fiber is extremely important for refining efficiency, fiber quality, and variability of the fiber going to the paper machine. So we need to look at each one of these in detail, see where we're at, and see where we can be if we improved. But we'll start out with the first one, amps controls. So what the fiber is actually seeing is how much power per unit ton is being applied. And here's the kilowatts. Here's the actual power being applied. So with amps control, at the beginning of the motor load, you see that it's not changing much. So there's no easy way to know how many kilowatts you're applying because the power factor is constantly changing until you're about 80% loaded, and then it kind of starts fixing itself up. And if you come up with a weird formula that correlates this to this, then you can probably come up with kind of where you're at with how many kilowatts you're applying, but definitely not a good way to control refiners. So a step improvement is constant power controls. Here you see how much power is constantly being applied to the fiber. The downside to this is that as flow changes, you can see the flow changes here, because the power is constant, then the energy per unit ton fluctuates in the opposite direction. Less fiber, same power, more energy, and vice versa. So another step improvement that we made was net specific energy controls. Okay, now the amount of energy per unit ton is fixed. It's constant at all times. Everybody's happy. The flow changes, flow dips, so does power, and then the energy stays the same. So it's another huge step improvement and a much better way of controlling refiners versus constant power. Another step that can go on and improve refiner performance even further. Specific energy controls has its flaws as well. It pretty much does not take into account what kind of kappa variability, what kind of quick flow and consistency changes. The refiner is just not fast enough to react to all of that. And all it does is it grabs whatever is coming in and it changes it to something coming out, probably accenting whatever issues it had. So what we came up with was a specific freeness control where we're saying, okay, let's go further and look at the fiber length, for instance, or the actual freeness each step of the way and make sure that once it reaches this blend chest, here's a before on specific energy, once it reaches this blend chest, everything is completely uniform. And this is a 53% variation of fiber length at the blend chest improvement from specific energy controls going to freeness controls. So now we're looking at not only what's coming out of the refiner, but what was coming into the refiner as well. We're taking that into account where specific energy was not. So each one of those is a step improvement from the one before. Obviously, this is a building improvement from the amps controls, but from the step before, it's a great improvement in and of itself. So how do we make sure we're using these instruments properly? Well, there's the old traditional two-speed gear motor or the now new and improved VFD. So traditionally, there was a two-speed gear motor with exactly as it's called, two speeds. One was fast and one was slow. That slow speed was not that slow. So every time we would get close to the actual set point you put, it would surpass that set point and then have to hunt on the other side to try to reach that set point and hunt. So we had to open the bandwidth to plus minus 3% of full motor load. That's a lot of variation coming out of the refiner. With this VFD, the slow speed is about 1/10 of the speed of the traditional two-speed gear motors. So now we can go very slowly as we approach the set point and very slowly as we get away from the set point to make sure we're always circling that set point to about 0.5% deadband. On the counter side, you can overspeed the VFD by about 25%. What that means is that every time you want to put your refiner online or take your refiner offline, we're doing it 25% faster, meaning you have a lot of wasted pulp beforehand, a lot less wasted pulp after the refiner is taken offline. Then we want to make sure that the plates that are being used in the refiners are well taken care of. Again, as I mentioned a little bit earlier, these are critical components. They're your wear components, and they are the highest operational cost beyond the energy. So we talked a little bit about the spline saving energy and how we want to make sure that the refiner is in tip-top shape to make sure that they are operating efficiently. But we also want to make sure that the wear components have a great life. So this first component here is called an anti-plate class system. And what it is we have two accelerometers installed, one in each one of the stator positions, and they're measuring axial movement or vibration within the refiners. So every time there's plate-to-plate interaction, the accelerometers pick that up. They're tied back to the DCS. And our logic indicates, hey, let's open the plates up so that we don't continue having plate-to-plate interaction and you're just wasting plates instead of fiber-to-plate interaction. Or more importantly, if there's something passing through the refiner or if the refiner just has no flow through it and you're just plate-to-plate, it's going to avoid a huge catastrophic failure. So it's going to try this several times. Specifically, we program it to try this 3 times. If on the 3rd time of the plates releasing from the anti-plate clash system indicating that there's clashing, the condition is not eliminated, then the refiner plates are set to open completely, telling the operator, hey, go in there and check it out. Something is going to happen. So what the main function of this plate clash system is trying to do is avoid catastrophic failures. So if we keep wearing through those refiner plates, we're going to eventually weld them together, weld the refiner together, and you're going to end up changing out an adjusting mechanism, rotating assembly, or destroying the whole refiner and having to rebuild a very expensive piece of equipment in your mill. This is what the anti-plate clash system is trying to protect the plates. Over here we have the plate wear indicator, and what this is, it's a laser-based measuring device that's measuring the total movement and the total distance that the sliding head has moved inside. So we'll start out your refiners with new plates. We'll bring all 4 plate positions together as you would set your proximity switches. And then we're going to measure that. That'll be our 0 point. Once the plates start wearing in, this refiner plate wear indicator is going to start picking up the distance of how much that sliding head has moved in relative to a starting point. And that's going to give you the plate wear on these 4 positions. So this again is tied back to your DCS like the anti-plate clash system, and you're going to be able to monitor plate life. It's also going to be a good way of indicating when it's time to change your plates. You don't want to change your plates too early if there's still bar edges left and they're still usable. You would be wasting time and money in replacing the plates. You don't want to change them when it's too late because the same reason, you're going to have a catastrophic failure, or your refiner is just going to quit on you. There's no bar edges to do any work. There's no bar edges to do any pumping, and you're not going to get any pulp to your next chest. If you do, it's going to be unrefined. So the biggest difference between operating with this plate wear indicator and the traditional, is there a pressure rise across the refiner or pressure drop, is that this is only measuring the position of the plates at all times. The traditional, is there a pressure rise across the refiner? If the refiner is plugged, you're going to think, oh, it's time to change out plates, and maybe it's just plugged instead of completely worn. It's also dependent on flow. So higher flows are going to have less of a pressure rise across the refiner, and lower flows are going to have more of a pressure rise across the refiner. So what we're looking at is, this doesn't care about the flow. It doesn't care whether it's plugged or not. It's only looking at plate life. It's a great tool to make sure that the plates are healthy and operating how they should be. Again, this is a huge cost component in operations that you constantly have to be changing out. So we want to make sure it's optimized and its life is optimized, more importantly. So that takes us to the next step, and it's a huge step improvement. You're currently looking at your refiner from angles within the mill, and your operator's looking at it. Maybe the supervisor's looking at the refiner on a regular basis as well. Operations and making sure in the background. But we have an industrial internet. It's an excellent solution that we have, where we have a combination of process technology, services, and automation looking at your whole system. So we're grabbing all those instruments that I just talked about, this anti-plate clash system, this laser plate wear indicator. We're looking at your flow transmitters. We're looking at your power being applied in your refiners. We're looking at everything. And not only are we seeing that those are where they should be, but we're analyzing which point gave you the best results on the paper machine and saying, hey, if you operate at this point, we've seen that your paper machine, for some reason or another, behaves better. Or if you use this type of pulp or this combination, this is what's resulting on your paper machine. So we're analyzing all those parameters and putting them in a very complex algorithm and seeing which one is producing the best results. So all of that is a huge step improvement. And here's what we're looking at. We're looking at all the different characteristics. These are called dashboards. You're looking at a refiner dashboard. So with the industrial internet, we have the capability of doing this throughout the mill. Here I'm focused on the refining aspects of it. So here's what we're looking at. We're looking at all the different parameters going into the refiner, but we can also correlate this to whatever information you're willing to share or whatever instrumentation is available on the paper side, so that we can correlate what's happening in the refiners to what's happening each stage along the way. And the same can be said before the refiner. So we can look at the whole system and make sure that when we partner with you, there is a constant improvement in your operation. It's not a static, yeah, we're doing fine, this is where we were before. No, we're making sure it's not just somebody looking at what we did yesterday. It's what we did yesterday and how we can do that better approach. So now I want to bring all this together and how we partner to make this happen. So the next two slides, including this one here and the next one, are a bit complicated. So I'm not going to get into a lot of details, but once you guys request this information, it will be submitted to you and you'll have access to it. But here are some of the things we're looking at: mechanical audits, refiner audits, measurement audits, and then more importantly, this concept of connecting to the Valmet industrial internet, working together, where we contract all these services into one. So we can come up with a contract in which not only are we monitoring you from our industrial internet, but we're providing field services to make sure that what we're seeing is getting fixed. We're also making sure that your operators are being trained, your mechanical maintenance group is being trained properly to maintain that refining efficiency and refiner operation in top shape. Again, I'm not going to get into details. You guys will have this slide as requested, but here are all the different fields that we're touching on both the services and product sides that we can supply or we can help with in your refiner operation. This is the result of everything. So here I have closing the loop. Here's your starting point. You have an older refiner in operation. And what we want to do is take it to the next level. Instead of operating in amps, power controls, or specific energy, we want to go to the map queue and make sure that fiber length is optimized and that the freeness going into the paper machine is always the same, not variable, specific to each grade that you're manufacturing. That's a step improvement in and of itself. Then once we're seeing where we're at, we're going to say, hey, we can do that much better if you have a more efficient refiner. So here's your next step change, potentially rebuilding the refiner, or if it's vintage that doesn't make sense to rebuild, then replacing the refiner. And then we're going to make sure in our lab that the before and after is evaluated and proves that we did the savings, or we justified the savings that we indicated we were going to get to when we said we would replace one refiner with another and give you X% of energy savings or plate life or whatever it was that we discussed. We have our labs to test out before and after. Then we're going to take it to the next level, and we also have, through the acquisitions of GL&V and the acquisitions of J&L, now all one big happy Valmet family, we also have an abundant amount of refiner segments. We are the biggest supplier of refiner plate segments in the world. So we're going to take this to the next level and say, okay, we thought we were doing good, but we can do better. There's always a next step. And again, we're going to optimize plates and take it back to the lab. Let's see what each one of these plate trials did. Make sure we saw another step change improvement. And finally, we're going to partner with you and make sure that these improvements continue on forward. And we continue saying, change this, do that, and we're going to be with you each step along the way to make sure that those changes are getting you to a better, improved spot each step of the way. So last but not least, I just wanted to show, again, the combination of our refiners integrated portfolio, conical Conflow, the Pro refiner coming from the legacy Valmet side, and now the DD refiners coming from the legacy GLV side, all in one integrated portfolio. We didn't list the older model refiners, but the DD 2000, 3000, and 4000, Through the acquisitions of Beloit Jones by GL&V and now GL&V by Valmet, we are the OEM of DD line refiners, which is the most popular line of refiners in North America. And with that, I will give the floor back to Ward.
At this point, we're at the Q&A section. Thanks for the great presentation, Louis. Before we get into the Q&A portion of this webinar, let me say that this presentation is available in PDF format. Simply email Louis at louis.gonzalez@valmet.com, and he'll be happy to send you a copy. We received a few questions already, but you can still submit them during this Q&A period. If Louis can't answer them today because he needs more information or the question deals with confidential matters, he'll be sure to email you a comprehensive answer after the webinar. Louis, take it away for Q&A.
The first question we have is, what is the typical plate life you expect in your refiners? And this is a pretty loaded question, but the answer is that it's very dependent on the application. So some of the applications in which there's a lot of debris like OCC and recycled fibers, you're looking at somewhere between 30 to 90 days plate life. And again, that depends on the level of debris and your finished product, how much energy you're applying in the refiner. A higher kappa unbleached refiners are going to be somewhere in the 4 to 6 month range. And then bleached application where the fiber is not very abrasive and it's fairly clean. Unless something weird happens, you're looking at somewhere between 6 months and a year. It's, like I said, a loaded question. It's going to be very dependent. These are general ballpark figures for the different grades that I just mentioned. Specifics, it's better to take a reference of what your current plate life is and then figuring out if it's optimized for the particular application and estimating what it could be if we made some changes to, say, the design or the alloy of the refiner plate, optimize it that way. So good question. Second question I have here is, does Valmet still offer the refiner exchange program that GLV used to offer? And the answer is definitely. The acquisition of GL&V brought along all those benefits of the disc refiners that GL&V offered in the past. So we still have the biggest exchange program in the world. And what we try to do is keep one particular or each particular size and model refiner a complete unit readily available for exchanges. So as I mentioned earlier, you crash a refiner, or it's time to overhaul it, it's time to rebuild your refiner completely. We generally try to keep one in the shelf so that we can send that out. You send us the old shell and you exchange your refiner, or in essence completely rebuilt your refiner. Then we'll refurbish, rebuild the one you sent us and have it ready for another customer. So the answer is yes, and we do this also with components like rotating assemblies, adjusting mechanisms, packing boxes. Some of the smaller components are not worthwhile rebuilding, but yes, we have this available still as Valmet. Another good question. Well, I have another question here about when applying freeness control, how and where do we measure freeness? I'll take that into a two-part question. There's a second portion of it. And the answer is that the system capabilities are such where one unit can handle 20 sample points, and the samples take at max 3 minutes. That's considering the full stage of taking the sample, analyzing the freeness, putting out the number, and then recalibrating itself. So it completely cleans itself out and recalibrates itself. So we're looking at analyzing the freeness either before and after the refiner, or before and after each refiner, but most importantly, at the blend chest. So if you have multiple fibers going to the blend chest and you're trying to adjust the freeness on each particular stream going out, but then at the blend chest you're changing the ratios, the ratio at the blend chest is obviously going to be all over the place because you are adjusting freenesses for each one, but the ratios change. So we're looking at optimizing at least the blend chest one, but again, we have up to 20 sample ports connected to a single unit, and the time for sampling is 3 minutes roughly. So we can do this where we're analyzing the outlet of the refiners twice every 9 minutes and the inlet once, or we can do it where, the more critical ones like OCC, which is constantly changing inlet freeness, we're analyzing more than, say, a high kappa combination that you're using craft and OCC mix. We'll analyze the one that's more variable a little bit more than the other one. But the answer is we can put these sample ports pretty much anywhere, and up to 20 of them. Then it says a sampling system based on an analyzer would provide too slow measurements, even if it compromises the primary loop and the cascade control. So again, the most important point that we're looking at is the blend chest. So we're going to make one of the refiners more of the driver than the other refiners to make sure that once this change happens on the blend chest, we can change that very quickly by going, you're definitely right, the loop is not going to be fast enough to pick everything up, but it's going to be a lot faster at picking stuff up than a specific energy control, and that's just going to transfer whatever issues you had at the beginning onto the end product and compromise everything going forward. So the answer to that one is definitely cascade control has to be very quickly, but it is a good tool of assuring that the amount of energy is something that you understand as well. It's not just changing power and going from there. It's just a final tool of saying, okay, this change required this amount of energy going forward. So it's another good point. Let's see, have another question here. What percent of bar height is acceptable? It's another good question, and this is very dependent on where your refiner is at. So with this refiners, the wear is in the Z position, so it's going inside the grooves, so you're wearing more and more into the grooves. So there is no change in refining intensity, resulting refining intensity. So as long as you have enough bar to get the refiner to, as long as you have enough bar to get the pulp to the next chest, there is no issue with continuing to refine. So the answer is close to 0% bar height left if you can pump. And again, it's going to be very dependent on how far your next chest is and how much pulp you're going through there. So if you're at the higher end of the pumping curve on the refiner, you're going to have to change plates with the bar still pretty high, because as you start wearing into these, there's not going to be a lot of pumping capacity left. When comparing conical versus DD refiners, what is the use for each one? We're still in the process. Like I said, we just got acquired by Valmet. I come from the GLV side, and one of my first biggest points has been this comparison of conical and disc refiner, specifically the three technologies that I showed at the end, to see which one impacts fibers which way and which one has the best efficiency on what particular fiber. So it could be the case that one refiner performs better than another. So like you mentioned in this question, comparing the two, which one is better for which application. We're in the process, actually, 3 weeks ago, we did trials with the 3 units on bleached eucalyptus, and last week we did bleached softwood. So we are in the process of trialing these at different refining conditions. We have not gotten the results yet, but it is something that we are evaluating. So technically, the answer is, I don't know, honestly. The 3 refiners are excellent. The DD6000 is the best disc refiner in the field. And the conical refiners, we really have no competition on that end. So they're all great refiners, but which one is better for what? We're still in the process of working that out. The next question is, does Valmet offer refiner audits to identify all of the items that need to be repaired to optimize performance? And how long would an audit take? So yes, the answer is absolutely. We offer both mechanical and process audits. how long would the audit take? So we can inspect on the mechanical side 3 refiners per day. So if you have an outage and you have 12 refiners, we're probably going to be able to get all 12 refiners within 4 days. What we provide is the supervisor with the experience to indicate to at least 2 millwrights that you're going to have to supply with him. He's going to be giving them directions on what to do, and then he's going to generate a report on what he found mechanically wrong with the system or with the refiner, and what needs to be done to get it back to OEM conditions. So it's going to be very specific. We're going to identify whether it's a rotating assembly issue, whether it's a tram alignment issue, and generally if we find a tram alignment issue, we're going to fix it right in place. So we're going to tram your refiner as long as you're willing to work with us. And some of these trammings take a while because at the end of the tramming you've misaligned your main motor as well. So you're going to have to be willing to realign that main motor as well. But we're willing to do this with you. And again, that takes about 1/3 of a day per refiner. So we can definitely hit at least 3 to 4 refiners if we have the right crew in place. On the process side, we collect a lot of the information before we get to the mill. So we're asking for things like flow, consistency, applied power, inlet and outlet pressure, plate designs. And then we come up with a report that indicates where you're at today on the process side with your existing equipment and where you could be if you optimize by, say, upgrading to spline technology, changing out refiner configuration, changing out refiner plates, stuff like that. And that will take us probably about a week to gather all the information. We'll generate the report within the month. It does take a little bit because it's time consuming on our end. It's usually 2 months worth of data that we're looking for to make sure that we're looking at each refiner properly and not just a snapshot of what's going on at that particular moment that we're visiting. So it takes a little bit to analyze all the data, break it down, and put together a report, but I'd say a good month on the turnaround for the report, but a week of actual audit, maybe a couple of days visit to the mill to discuss with you what kind of issues you want us to look for, and if there's anything you need us to take into consideration going forward. If the goal is to increase production or anything like that, we want to make sure we take that into consideration before making any recommendations. So running short on time here, but I'll try one more here. How long should the spline rotating head and hub last worn splines before they need to be replaced? And what would make them wear faster than normal? Okay, great question. So we're looking at for applications where the level of debris is high, somewhere in the 3 to 5 year range per side. So OCC applications for test liner, for instance, the level of debris, the amount of sand in there is fairly high, and the only lubrication that the splines have to float on top of each other is the actual process. So they're seeing that sand on a regular basis. So we're looking at about 3 to 5 years for that type of furnish and that type of application before you flip it around. So total is going to be 6 to 10 years for that type of application. For linerboard applications with virgin craft, you're probably looking more like 5 to 7 years for a total life of 10 to 14 years. And then for bleached application, it's pretty much endless. We've seen installations where we've had these for 15, 16 years, and the customer hasn't even flipped the components yet because there's no wear shown on any of the spline components. It's highly dependent on application. But to the second point, what makes the wear faster than normal? So the tram that I mentioned earlier, if the shaft is not properly perpendicular to that refining surface that I mentioned, that door datum, that's the critical spot that we need to make sure that all plates are parallel to that. If you can imagine, as I mentioned earlier, the pressure on both sides of that rotor is going to try to make it perfectly balance itself on the, it's going to perfectly balance itself between the two stator positions. So if you can imagine that cocked like 15 degrees, for instance, to over exaggerate, between the two surfaces, the pressure is going to push it on one side one way and on the other side the other way to try to straighten that rotor out. And remember that that rotor is fixed to the shaft. So now you have these spline teeth pushing against each other, the rotor against the hub, it trying to align itself, it trying to straighten out where the shaft is just not straight to begin with. So the splines are going to start eating into each other. And again, obviously, the process is the second factor. It's the biggest factor. It's the only lubrication point. So if you have, if you're using some white waters in which, for instance, to throw out a random example, some cement applications and the white water has bits of cement in there, or some contaminants with high abrasiveness going through the system, and this is what you're using as your dilution water, then that is also going to impact refiner spline life. I hope that answers that question. I will give it back to Ward here because we're running out of time.
Yes, we are, but they were some great questions. I hope we were able to respond to most of, if not all, your questions. Lewis will follow up via email with anyone whose question we were unable to answer. We'll also be emailing you a link to the recorded webinar as soon as it's available on YouTube. If you have any further questions, email them to luis.gonzalez@valmet.com or reach out to him at LinkedIn, and he can go more in depth with you about any refining, deflaking, dispersing needs you may have. We hope you've gained some valuable knowledge about maximizing your refiner performance today that can help move your mill forward. Thank you for giving us your time today, and we hope you'll join us at future Valmet webinars. Bye-bye.